Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the binary search algorithm. This is a very famous searching algorithm. It's not very difficult to understand, to be honest. In fact, you've probably applied the logic behind binary search in real life before. But that being said, it's a very important algorithm, and it's very important that you understand it completely. Both how to implement it and how the algorithm works in terms of space and time complexity. In an interview, you might be asked to implement binary search directly, or you might be asked a sort of more difficult question that uses binary search and that requires you to know how to implement binary search. So with all that being said, let's dive into the algorithm and how it works. Or I guess I'll start by giving you an example of how you might have used binary search in real life. So let's imagine that we have a professor. Maybe you're a professor in a college class, and you've gathered a bunch of essays written by your students. And every essay has at the top of the paper the name of the student that wrote it. Or let's just say the first name. And all the essays are piled up in one big pile, and they're sorted alphabetically by the names of the students. So at the top, you've got all the students whose names start with A, and at the bottom, you've got all the students whose names start with Z. And now you want to find the essay written by me, Clement, right? My name starts with a C. How might you go about finding the essay written by Clement? So you could just kind of start at the top and go through all of them until you get to Clement, but probably a better way of doing this that you would do in real life would be you cut the pile in two and you look at the essay in the middle. And depending on who wrote the essay in the middle, you then search one of the two remaining piles. So if you cut the pile in two and the essay in the middle is written by someone named, let's say, Monica, then you know that all the essays in the top pile will be written by people whose names start with the letter M or a letter that comes before M in the alphabet. And everybody in the other pile has a name with a letter that starts after M in the alphabet. So what that means is you can eliminate the entire second half of essays because you're looking for the essay written by Clement. And so then what you can do is you can take that top pile where you know my essay has to be, and you cut that pile in half again. And the essay in the middle there might be written by someone named David. And so you can continue on like that, eliminating half of the pile every time. And you've probably done this in your life before in some way, shape, or form. And that is how binary search works. So now, if you're confused, let's dive into an actual example with an array of numbers. So here in front of me, I've got an array of numbers. They're all integer values. And you'll notice that they are sorted because that's pretty much the main thing or prerequisite to binary search. It's that the list of things that you're going to be applying binary search on has to be sorted. Okay, so if it's not sorted, you cannot apply binary search. If it is sorted, you can. And so a quick tip here, if you're ever in an interview where the interview question gives you a list of things that is sorted, you might want to ask yourself if binary search could be used in some way to solve the problem, because a sorted array or a sorted list of things tends to point to binary search. Now, going back to binary search here, we've got an array of numbers, and we've got a target number, the number 33, that we want to find in this array using binary search. It turns out that it's here. It's the fourth number in the array. So how does it work? How does the algorithm actually work? The thing you're going to want to do is you're going to want to find the middle number in the array, right? And based on that middle number and how it compares to your target number, you're going to continue exploring either the first half of the array or the second half. And so to find the middle number, you're going to declare or initialize a left pointer and a right pointer. So I'll write them here. I'll write a left pointer, denoted by the letter L, that is going to point to the first number in the array, which happens to be 0 here. And then we're going to write we're going to initialize a right pointer that I'll put here in green. That's going to point to the last number in the array, which happens to be 73 here. And we're going to grab the indices of both of these numbers. So the index at which we have the number 0 is the index 0, right? Because it's the first number in the array. So our left pointer is pointing at the number at index 0. And in fact, I'm actually going to write all the indices above so that we have them easily. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And so that means that our right pointer is pointing at the number at index 9. And so now to calculate the middle number, what we're going to do, and I guess I'll write the middle number, I'll denote the middle number, the middle pointer with the letter M, and I'll write it here in the middle. M is going to be equal to, and actually let me give myself a bit of space, M is going to be equal to the sum of the index L plus the index R divided by 2. In other words, we're taking the average of these two pointers. So it's going to be 0 plus 9, right, which is L plus R. And then that sum is going to be divided by 2. And now, because we're dealing with indices, we don't want the index to be a decimal number. So in this case, we're going to have 0 plus 9 divided by 2. That's 4.5. 4.5 isn't a valid index. That would just bring us like here in the very middle of the array between two numbers. So we're going to round this number down. Okay, and I'll denote the action of rounding down the same way that we do it in Python 3.5, which is just 2 slashes. Okay, so 0 plus 9 divided by 2 rounded down. And so that's going to make our middle pointer be equal to 4. Okay, so we can put our middle pointer. Let me move this formula here a bit to the bottom to give us a bit of space, and we can put our middle pointer here to point to the number at index 4, which is 45. And so now that we have the middle number, we compare it to our target number. So we compare 45 to our number 33. Okay, so is 45 equal to 33? Have we actually found our number? No, we haven't. Okay, so we're not done. We have to continue exploring. But is 45 greater than or lesser than 33? Here it happens to be greater than 33. So what that means is that every number to the right of our middle number, every number here to the right of 45, is naturally going to be even greater than 33, or even greater than 45, and so greater than 33. And so we can eliminate all these numbers. And so what we can do now is we can erase our middle pointer and move our right pointer. So let me grab our right pointer here, move our right pointer to point to the index right next to our middle pointer. So I guess actually I'm going to undo what I just did to make this more clear. Let's erase here our calculation of the middle pointer. And we have the middle pointer pointing to index 4. We're going to grab the right pointer and move it to the index 1 to the left of the middle pointer. Okay? And now we can erase the middle pointer. And we can basically say that we have crossed out this entire right half of the array. We're never going to explore it again. And now we recalculate the middle pointer. So we say M is going to be equal to 0, which is where we have the left pointer, or here, this left index, right? Plus 3, because our right pointer is now pointing at 3. So plus 3. And then we once again divided by 2, rounded down. So 0 plus 3 divided by 2 is 1.5, rounded down is 1. And so now our middle pointer is going to point to index 1 here, which happens to have the number 1. So now we compare the number 1, which is the middle number of our sort of new subarray of 4 numbers. Compare the number 1 to 33, our target number. 1 is not equal to 33, so we're not done. We have to keep looking. 1 is smaller than 33, so that means that every number to the left of 1 must also be smaller than 33, since we're dealing with a sorted array. So what we can do is we can grab our left pointer this time and move it 1 position to the right of the middle pointer, which is here. We can erase our middle pointer, and we can cross out this entire left section of the array, which we've now eliminated. Okay? And then finally, we recalculate the middle pointer. So the middle pointer here, let me erase this, is going to be equal to 2 plus 3 divided by 2 rounded down, right? Because we have the left pointer pointing to 2, the right pointer pointing to 3, and we're dividing it by 2. So that's going to be 5 divided by 2. That's going to be 2.5. And rounded down is going to be 2. So now we've got a middle pointer pointing to the same number as the left pointer. That's the number 21. So we compare 21 to 33. 21 is not equal to 33, so we're not done yet. 21 is less than 33, so that means that we can move the left pointer to the right here of the middle pointer. So we move it by 1. I kind of cut it off here. And now we've got our left pointer, which is overlapping with our right pointer. And we can eliminate the middle pointer, or we can erase it, and we can eliminate this entire half of our 2-number array, which is just one number, the number 21. And so now our left and right pointers are overlapping each other. They're both pointing to one number, so that's going to be our middle number. If we apply the formula, we just do 3 plus 3 divided by 2, that's 3. And here, 33 happens to be the number that we're looking for, so we are done, and we can return the index that we're looking for, right? We can return index 3. That's where 33 is located at, or positioned. And that's how we found the number 33 using binary search. We initialized these 2 pointers, the left pointer and the right pointer. We kept calculating a middle pointer, and we kept eliminating half of the array depending on where our target number would be positioned compared to the middle number. And so now I guess what would be interesting would be to redo this example really quickly. We'll go a bit faster this time around with a number that's not going to be in the array. So I guess let me just circle this number 33 to show that we found it. And now if we rewrite the array here below our first array, so we've got 0, 1, 21, 33, 45. We've got 2 45s, 61. And this time what we're going to do is we're going to look for a number that's not in the array. So let's say the number 74, okay? So 74 is not in the array. We start by initializing our left pointer and our right pointer. We calculate the middle. So the middle is going to be 0 plus 9 divided by 2 rounded down. So that's going to be 4. That's the same index that we had earlier at the beginning. So we can put our middle pointer to point to 4. So we put it here. Now that's the number 45. 45 is less than 74. So we can eliminate this entire left half, and we can move our left pointer here to the left of the middle number. Now we can recalculate the middle number. So m is going to be equal to, 5 plus 9 divided by 2. So 5 plus 9 divided by 2, that's going to be 14 divided by 2, that's going to be 7. So the middle number is going to point to 7, that's 71. Compare 71 to 74. 71 is less than 74, so we eliminate this entire half. we can move the left number or the left pointer here, recalculate middle to be this time around 8 plus 9 divided by 2. So 8 plus 9 divided by 2. 8 plus 9 divided by 2 is going to be what? 17 divided by 2. That's going to be 8.5. So our middle pointer, or 8 rather. So our middle pointer is now going to overlap with the left pointer. 72 is less than 74, so we eliminate it again. We move our left pointer now here to overlap with the right pointer. 73 is once again less than 74, and so now we're going to move the left pointer again to the right, and now the left pointer is going to be bigger than the right pointer. And when the left pointer is bigger than the right pointer, I guess I can erase this middle pointer here. When the left pointer is bigger than the right pointer, that's when we know we're done. We have not found the number in the array, and it cannot be found. And so at this point, we kind of stop everything that we're doing, and we're done with the algorithm. We can say that we haven't found the number. So that is how binary search works. Now, before we dive into the code walkthrough, let's dive into the complexity analysis. So the time complexity is something very important to understand. The time complexity is going to be O of log of n, where n is the length of your input array. It's the number of numbers in the input array. So why is it O of log of n? The reason that it's O of log of n is because we are eliminating half of our input at every time that we kind of traverse through our input. If you recall, when we had this array here, let's say when we were looking for 74, we started by eliminating this entire half here, right? We eliminated this entire half of the array. So we had an input of length 10, I think. I think that we had 10 numbers, right? Because we have 9 indices, but that started 0. So we've got 10 numbers, and we eliminated half of them, okay? Then the second time around, or during our second sort of traversal, we eliminated this entire half of the remaining 5 numbers, okay? 3 numbers out of the 5 remaining numbers. Then during the third traversal, we eliminated this entire half of the remaining 2 numbers. And so on and so forth. And so because we're eliminating half of our input every time that we traverse it, that gives us a time complexity of O of log of n. And that's the beauty of binary search compared to something like, just traversing an array from front to end, because that just takes O of n time, right? We could have looked for a number by doing that, but that would have taken O of n time because we would have to traverse all the numbers rather than eliminating half of them at every point. Now, the space complexity is going to be fairly straightforward, though the space complexity does vary depending on how you implement this algorithm. If you implement binary search iteratively, which is how you should implement it, to be honest, it's going to run in O of 1 space, because if you implement this iteratively, and to be honest, even if you implement this recursively, which is the second way you can implement it, you're never using additional memory to store stuff, right? You're not storing variables somewhere. You can do this all in place in the array, and all you have to do is kind of keep track of the number, the target number. But so that's O of 1 space. Now, if you implement this algorithm recursively as opposed to iteratively, then depending on your language, you might have a space complexity of O of log of n space because of the memory usage on the call stack, right? You're gonna have, if you implement this recursively, you're gonna have frames on the call stack that will be used up, and so that's gonna take extra space. And so that's why it's typically advised to implement an algorithm like binary search iteratively rather than recursively, so that you can enjoy this sort of constant space. With that being said, let's dive into the code walkthrough to see how both the recursive solution and the iterative solution look. All right, so we've got our binary search function defined. It takes in an array of numbers and a target number. And the first thing we're going to want to do is implement this recursively. And so we're going to want to keep track of the left pointer and the right pointer that we talked about during the conceptual overview of this video. So we might want to declare a sort of helper method, which we're going to call binary search helper. And this helper method is going to take in a left pointer and a right pointer. So in fact, this first method here is probably only going to return the result of that helper method. So binary search helper, and this binary search helper is going to take in the same array, the same target, but it's also going to take in a left pointer and a right pointer that are going to be initialized to 0 and to the final value in the array, or the final index in the array, which is going to be len of array minus 1, right? The last index in the array. And so now we can implement this binary search helper, which is going to be kind of the bread and butter of our algorithm. So it's going to take in an array, a target, a left pointer, and a right pointer. And the first thing we're going to want to do is check if we are at the sort of base case of our recursive algorithm, which is the left pointer greater than the right pointer? Recall that in our second example during the conceptual overview, when we were looking for the number 74, our left pointer eventually surpassed our right pointer. It was greater than our right pointer, and so we were done, right? So we can say if left is greater than right, then we're done, and we can just return a -1. Or you can ask your interviewer what you want to return if you can't find the number. And then what we can do is we can start, if we're not in this case, we can start by calculating the middle pointer. So middle is going to be equal to left plus right divided by 2 rounded down. So in Python 3.5, we can just do this double slash here. If you're working in JavaScript, you're going to do math.floor. Kind of depends on your language here. Make sure that you round the value down. And so now we can declare our potential match variable, which is just going to be the number in the array located at index middle. The index of the middle pointer is pointing at. And so then we can just compare our target to the potential match. So if the target is equal to the potential match, then we want to return the middle pointer, the middle index, because that's our answer. So that's another sort of base case in our recursive algorithm. And then if it's not equal, but if the target is less than the potential match, then we want to return another call to binary search helper, to the binary search helper method. But this time around, we're going to pass in a different right pointer. So we're going to pass in the same array, the same target, the same left pointer, but we're going to pass in middle -1 for the right pointer. Why are we doing that? Well, remember, our target is less than the potential match, so we want to eliminate the entire right half of the array. So we move our right pointer one location or one position to the left of the middle pointer, which is middle -1. And then in the last case, in the else case, if our target is greater than the potential match, then we can return binary search helper of array target. This time we update the left pointer to be middle +1, and we pass in the right pointer. Because again, here we want to eliminate the entire left half of the array, so we want to move our left pointer one position to the right of the middle pointer. And we're done. This is our binary search, our recursive implementation of the binary search algorithm. It's going to run in O of log of n time, and it's going to run in O of log of n space. The reason it runs in O of log of n space is, as we mentioned in the conceptual overview, you are adding frames to the call stack, and that takes up memory, takes up space because of these recursive calls. And so we get O of log of n space. Now, if we want to implement this algorithm iteratively, it's going to be very simple. We can pretty much copy paste what we've written here and just change a few things. Instead of doing this if left greater than right return one thing here, we're just going to create one big while loop. And so we're going to say while left is smaller than or equal to right. In other words, while the left pointer is not greater than right, then we do a bunch of stuff. So we can kind of indent all this stuff here inside the while loop. And if we ever get out of the while loop, we return -1. That's going to be, if we ever get to a point where left is greater than right, then we get out of the while loop and we return -1. Otherwise, inside the while loop, we declare our middle pointer the same way that we did during the recursive implementation. Declare our potential match. If target is equal to potential match, return middle. And then here, instead of returning this recursive call, all we have to do is update the right pointer, which here in the recursive call, we updated it to middle -1. So here we can just say right is going to be equal to middle -1. And we can delete this line. And here we can say else left is going to be middle +1. And here we can delete that line. And that's it. Now we've got our iterative algorithm. To be honest, we don't even need this helper method. We could have done all of this in our main method and initialized the left and right pointers there. That doesn't really matter. We can still keep this sort of format. But now here we've got a while loop, and we've got a middle pointer, we've got our potential match, and we just keep updating the right and left pointers until we either find our target or until we break out of the while loop and we return -1. And so this implementation of the algorithm is going to run in O of log of n time, but it's going to run in O of 1 space, which is a lot better than the recursive implementation. That's it for binary search. I hope that you now are very comfortable with the algorithm. I hope that you'll be able to implement it during any interviews. And I'll see you in the next video.